Welcome back to the course Basics of Mechanical Engineering 3. I have brought another tutorial session on the topics which are covered in the last 2 weeks, which are heat transfer, mass transfer and applications like boilers, etc. I will also take some numericals on calculating the efficiency of them. I am Dr. Amandeep Singh Gubroy from IIT Kanpur, and this tutorial session will focus on heat transfer. Heat transfer, if you recall, we talked about heat transfer modes, which could be conduction, convection, radiation. Conduction, when we talked about conduction between plane wall, conduction through cylinder. I will take numericals on them only. To recall the concept of conduction, conduction refers to mode of heat transfer in which heat flows through the material medium, and that occurs without actual migration of particles of medium from a region of higher temperature to a region of lower temperature. Heat conduction occurs by a migration of molecules and more effectively by the collision of molecules vibrating around relatively fixed positions. This is the mechanism which is already discussed, mechanism of conduction, that is, it is transfer of molecules. Here is one example given. When we heat a rod directly from here, you can see this is the hotter part or hotter region I would call. From the hotter region we are going towards the colder region and heat transfer is happening. So, this heat transfer is through conduction, that is, this is direct material and what is being transferred here is molecules. I would call it as migration. Heat transfer rate by conduction is governed by Fourier's law. It states that rate of heat flow by the conduction through a uniform or fixed material is directly proportional to the area normal to the direction of the heat flow and the temperature gradient in the direction of heat flow. So, temperature gradient, that is what is the difference in the temperature, and the area, that is normal to the direction of heat flow. What is the area? For example, if it is a plate being put here of a smaller cross section, heat transfer would be less. If it is a higher cross section plate, heat transfer would be more. I am talking about the cross section, that is the area that is normal to the direction of heat flow. So, let me now recall the relations between the heat transfer rate, that is Q, for the plane wall. For a conduction plane wall, that is with uniform thermal conductivity, heat transfer rate is given by Q is equal to K A times delta T by X. Delta T, where is the temperature difference across the material in Kelvin or in centigrades. For example, this is T1, this is T2, T1 is greater than T2. From the hotter area, that is T1, heat transfer to the colder area. So, there is a material, this material which you could see these green lines, this is the material property, that is the thermal conductivity of the material. The material property here is thermal conductivity of the material, which is in watts per meter Kelvin. So, each material has thermal conductivity. For example, copper has very high thermal conductivity, aluminium is little lesser than that, mild steel is little lesser than that, aluminium itself. So, conductivity or coefficient of thermal conductivity is an important factor and it is directly proportional to the rate of heat transfer. Now, here delta T is discussed, K is discussed. What is A? Area, as I discussed, is a cross sectional area normal to the heat flow, which is in meter square. Now comes X. What is X? X is thickness of the material in a direction of heat flow, which is given in M. It is given in meters here. This could be also written as Q is equal to delta T by R, where R is thermal resistance. When we substitute the value of R as X by K into A, this becomes delta T by R as the rate of heat transfer, which is in watts. Let me directly come to a problem statement so that we understand the concept better. The problem statement says calculate the rate of heat lost for a red brick wall of length 5 meters and height 4 meters. Thickness of the wall is 0.25 meters. The temperature of the inner surface is 373 Kelvin and of the outer surface is 303 Kelvin. Thermal conductivity of red brick is 0.7 watts per meter Kelvin. Calculate the temperature at the interior point of the wall 20 centimeter from the inner surface. Very interesting problem. So, here what they are asking is we need to calculate or find the temperature at the interior point of the wall, an interior point which is 20 centimeter from the inner surface. So, it is the wall that is being mentioned in the problem statement. This wall has the inner surface temperature at 373 Kelvin. If I call this left side as inner surface and this right side as the outer surface, and on the outer surface the temperature given is 303 Kelvin. K for this wall, that is the coefficient of thermal conductivity, is given as 0.7 watts per meter Kelvin. Heat transfer happens from left to right and this thickness of the wall is given as 0.25 meters. Now, problem is what is the heat transfer so as the temperature at the interior point, an interior point which is 0.2 meter. So, what is temperature here? When heat transfer happens from the hotter to the colder portion of the wall, this is Q. Now, it has been given that length of the wall L is equal to 5 meters, height is equal to 4 meters, thickness is 0.25 meters. I call it T, or I could even call it as X as it was given in the formula above. X is thickness of material in the direction of heat flow. Then temperature T1, which is the higher temperature, is 373 Kelvin. The low temperature of the other side of the wall is 303 Kelvin, and value of K is also given as 0.7 watts per meter Kelvin. Now, heat lost to calculate, that is the first part. Calculate the rate of heat lost for the red brick. So, first part, that is heat lost. This is to be calculated. For this, let me just put the relation Q is equal to K A delta T by X. So, for the area, I have to calculate, or I will put the values of area as such. For example, K times area is length into height, because this is the area which is normal to the heat flow, the cross sectional area, that is length into height. Then delta T is what? The difference in temperature, that is T1 minus T2 by X, that is thickness. Substituting all these values, K is 0.7 watts per meter Kelvin. Length and height are 5 meters and 4 meters respectively. T1 is 373 and T2 is 303 Kelvin respectively, and X is 0.25 meters. If I calculate this, my value turns out to be 3920 watts of heat loss, because on the other side there is a colder wall. Now, temperature at 20 centimeter from the inner surface. Temperature at 0.2 meters, which is 20 centimeters from inner surface. Inner surface, that is the hotter surface, it says. Now, this we can calculate using the similar relation. Only we will substitute the value of x here as 0.2. So, what is Q in general? It is K into A into T1 minus, I will call this temperature as T, which is to be determined. This is T, it is to be determined, and here the value of x1 I will call it as, which is 2 meters. So, to find the value of T, I would have to put it in this way: T1 minus T is equal to x1 into Q by K into A, or we can put it in a way: T is equal to T1 minus this relation x into Q by K into A. Putting the values, T1 is 373 Kelvin minus x1 is 0.2 meters, Q is calculated here, which is 3920 watts, K is the coefficient of thermal conductivity, which is given as 0.7, and area is length into height, that is 5 into 4. So, this gives me the temperature as 317 Kelvin. This is the temperature at 0.2 meters from the inner wall. So, we have gotten both the values here. This temperature that is calculated here is 317 Kelvin, and heat lost Q, this is calculated as 3920 watts. These are all calculated. This is also calculated or determined. Another interesting problem statement is here on conduction in plane wall, which says what thickness of an insulation material which has thermal conductivity of 0.2 watts per meter Kelvin is required for a wall with an inner temperature of 500 Kelvin, outer temperature of 280 Kelvin, and if the maximum allowable heat is 110 watt and length of wall is 0.5 meters, assume the wall length is twice its breadth. So, this is also a wall, a plain wall, in which it says length is twice its breadth. For example, this is length here, I call it as L, and thickness is x, a length of wall is given as 0.5 meters. Also, the temperature is given, temperature, the inner temperature is 500 Kelvin, this is 500 Kelvin, outer temperature is 280 Kelvin, this is inner surface and this is outer surface. Other parameters are, we have K 0.2 watts per meter Kelvin. Now, I will just put the value which are given, that is K is given as 0.2 watts per meter Kelvin. Temperature T1, which is high temperature, is 500 Kelvin. T2 is 280 Kelvin. It says heat loss is 110 watts, maximum allowable heat loss. That is, I have gotten the value of Q max, which is 110 watts. Length is given as 0.5 meters and breadth B is 0.5 by 2, that is 0.25 meters. Now, thickness of the wall X is to be calculated, because it asks what thickness of an institutional material. This is the question. But to calculate the thickness, I will just substitute the value here. Since Q is equal to K A T1 minus T2 by X, so I will put X as K A T1 minus T2 by Q, which is equal to length into breadth. If I put the values here, the K is 0.2, A is 0.5 into 0.25, T1 minus T2 would be 500 minus 280 by Q. Q is given here as 110 watts. I directly get the value of X as 0.05 meters, which is my thickness, which is equal to 5 centimeters. So, it is a 5 centimeter thick wall. So, this value of X here, that is calculated, this is equal to 0.05 meters is equal to 5 centimeter, and this is the calculated value. Now, this was about a plain wall. Let me now take the conduction problem statements for composite wall. What is a composite wall? To recall, the composite wall exists with more than one walls which are having different thermal conductivities. The thermal heat transfer is given as Q1 plus Q2 plus Q3 from the Fourier's law of conduction. Q is equal to Q1 plus Q2 plus Q3. Here in this case, Q1 is between T1 and T2, temperature T1 minus T2 by X1, which is the thickness of the first wall. Another wall attached to this first wall is with the thickness X2. And here the hotter temperature is T2 and the colder temperature is T3. So, T2 minus T3 comes into play here. Similarly, there is a different thermal conductivity, that is K3 here for the third wall, in which T3 is higher than T4 and the thickness is X3. So, this becomes my third wall. So, this gives me Q is equal to T1 minus T4 by X1 by K1A plus X2 by K2A plus X3 by K3A. This Q is equal to T1 minus T4 by R1 plus R2 plus R3. That is why this term R was given there in the previous slides. So, this Q turns out to be T1 minus T4 by R, where R is thermal resistance. For a composite wall with different thermal conductivities, Q is equal to Q1 plus Q2 plus Q3. Let me take a problem statement now here. A surface wall is made up of 3 layers. It is fire brick, insulating brick and red brick. The inner and outer surface temperatures are 1173 Kelvin and 303 Kelvin respectively. The respective coefficient of thermal conductivity of the layers are 1.2 watts per meter Kelvin, 0.14 watts per meter Kelvin and 0.9 watts per meter Kelvin, and the thickness of 20 centimeter, 8 centimeter and 11 centimeter, assuming close bonding of the layers. At the interface, find the heat loss per square meter and the interface temperature. So, this is first, this is second question that is asked. So, now we have been given a composite wall with 3 layers, and they say temperature at the inner surface, we have inner surface in the left and outer surface at the right. The temperatures given are, we have 1173 Kelvin towards the inner surface and 303 Kelvin towards the outer surface. That is, if I call this as T1, this is T4, that is the drop temperature. The temperature drop in the composite wall is not constant, it is at some rate here. Then the rate varies for the second surface, then the rate varies for the third surface. This is how the temperature drop here is. And here we have 3 different cross sections. This is a composite wall of which we have been given the thicknesses, that is x1, x2 and x3. This is 0.2 meter, that is 20 centimeter. This is 8 centimeter, that is 0.08 meter. And third wall is 11 centimeters, that is 0.11 meters. And they have given it as fire brick, insulating brick and red brick. This is fire brick, this is insulating brick, and this is red brick. Right? So we have x1, x2 and x3 here. This is x1, this is x2 and this is x3, the 3 thicknesses which are given. Now they ask, what is the heat loss per square meter? So there is transfer of heat from the left to right. Here it is Q, and we need to find the interface temperatures. Though temperature T4 is given, temperature T2 and T3 is to be determined. T2 and T3, this is to be found, this is to be found. Now, we have been given, let me put all the variables which are given. T1 is equal to 1173 Kelvin, T4 is equal to 303 Kelvin, K1, that is thermal conductivity coefficient, is 1.2 watts per meter Kelvin, that is given here, 1.2 watts per meter Kelvin. K2 is 0.14 watts per meter Kelvin. K3 is 0.9 watts per meter Kelvin. X1, X2 and X3 are 0.2 meters, 0.08 meters and 0.11 meters respectively. Since we need to find the heat loss per square meter, so I will take here area as 1 meter square. Now, let me see heat loss per square meter. Let me say R is equal to R1 plus R2 plus R3, and this R, from the relation we can see it here, is X by K into area. So R is X1 by K1 into area plus X2 by K2 into area plus x3 by k3 into area. Area I have already taken as 1 square meter. Value of x1 and k1 I will substitute here. x2 and k2 values would also be substituted here. x3 and k3 values. This gives me value of R, that is thermal resistance, as 0.8603. Therefore, Q, that is heat loss, that is T1 minus T4 by R. If you recall this relation, this is heat loss. This could be calculated as putting the values. T1 is 1173 minus T4, that is 303, by the value of R, that is 0.8603. I got the value of heat loss as 1011.27 watt per meter square. It is important to note here that the units of Q here are put as watts per meter square, because in the question it is asked find the heat loss in per meter square units, that is heat loss per meter square. Also, because the area A is equal to 1 meter square, that is why these units have come. Now, next part here is interference temperature. So, we will calculate the interference temperature. First part here is fire brick, then we have insulating brick, then we have red brick. So, for the fire brick, we have the initial temperature, the final temperature T2 is to be determined. Now, we say for the fire brick, Q is equal to K1 into A into T1 minus T2 by X1. This will give me T1 minus T2 is equal to QX1 by K1A, and T2 would be T1 minus QX1 by KA. Here K is K1, K1A. Putting the values, T1 is 1173, Q here is calculated, it is 1011.27 into X1, that is 0.2 by K1 into A. K1 is 1.2 and area is taken as 1 meter square. So, this gives me the value of T2 as 1004.5 Kelvin. This is T2, right? First part is calculated. A portion of second part is calculated. Now, we need to find T3. Now, here we have gotten T2 as 1004.5 Kelvin. This is T2. T3 is still to be determined. For T3, we will take the insulating brick. In the insulating brick, what do we have? That is between T2 and T3. For the insulating brick, I'll just put the same relation. Q is equal to K2A into T2 minus T3 by X2. In a similar fashion, I'll find the value of T3 as I did it for T2, and T3 value here comes out to be 426.5 0.58 Kelvin. This is another calculated value. Here it will do the same steps as we did here. These same steps would be repeated here. So we got the value of T3, that is the interference temperature between the insulating brick and the red brick, as 426.58 Kelvin. With this, the questions asked in this problem statement, that is heat loss per square meter, is done, and interface temperatures or interference temperatures are also done. We call it interface because it is interface. Interference because there is an interference of temperature here between wall 1 and wall 2, that is between fire brick and insulating brick. So there is a connectivity. That is why I use the word interference here. You could also call it as interface temperature. So these words are being used interchangeably in some of the books. Next comes plane cylinder. We talked about the wall, we talked about the plane wall, we talked about the composite wall. Walls have the area as length into breadth in general. Now when we talk about cylinder, we have diameter. We need to determine the area. The pi r square or pi d square by 4 will be the area of the cylinder. This relation would be used in cylinder. Now for a plane cylinder with uniform thermal conductivity, the thermal resistance R is given by R is equal to log of R2 by R1 into 2 pi Lk, where L is length of the cylinder, R1 and R2 are the inside and the outside radius. Therefore, heat loss is given by 2 pi Lk into T1 minus T2, that is the difference between the temperatures T1 and T2. T1 is the inner temperature, T2 is the outer temperature, by the natural log of R2 by R1. So this relation you have studied or taken or seen in the lecture series as well. I will now directly prompt to the problem statement so that we try to understand this problem better. A metal pipe of 10 centimeter inner diameter and 15 centimeter outer diameter with a thermal conductivity of 45 watts per meter Kelvin is there. The inner and the outer surface temperatures are 100 degrees centigrade and 30 degrees centigrade respectively. Calculate the heat loss per unit length of pipe. So we have a pipe here, like it was given in the figure in the previous slide. We have a pipe here. I will just draw this cross section of pipe. This cross section of pipe here is somewhat like this here. So the cross section is somewhat like this. We have inner diameter, we have outer diameter. This is a solid pipe. Here it has been given the inner diameter and the outer diameter. If I say inner diameter, from here, this is the center point, I can have this radius R1. R1 is half of the diameter, that is 10 centimeters the diameter, that is 0.05 meters would be the value of R1. Similarly, R2, it is outer, 15 by 2 is 7.5 centimeter, 7.5 means R2 is equal to 0.075 meters. And it says that the temperature inside and outside are given, which are temperatures of 100 degrees centigrades and 30 degrees centigrades respectively. So there is heat flow from the hotter inner of the cylinder to the colder outer, that is heat flows in this direction Q. We have Q in Q coming outside of the cylinder. the coefficient of thermal conductivity, K value here, K is equal to 45 watts per meter Kelvin. So, everything that is given, D1, D2, that is 10 centimeters, D2 is 15 centimeters. This gives me R1 as 5 centimeter, that is 0.05 meters, R2 as 7.5 centimeter, that is 0.075 meters. Then temperature T1 is 100 degrees centigrades, temperature T2 is 30 degrees centigrades, value of K is 45 watts per meter Kelvin. Length of the cylinder is also given. This length here, this is length of cylinder, which is 1 meter. Why do I say length as 1 meter? Again, like the previous question, they have asked heat loss per unit length. Like in the previous question, they asked the heat loss per square meter. When they say per square meter, I took area as 1 meter square. Now they asked about per unit length here. I will take length as 1 meter. Now, using these all values, putting or substituting into the formula or the relation that we see for R here, I will try to calculate the thermal resistance. And then from thermal resistance, I will find the heat loss per unit length. Now we know Q is equal to delta T by R, right? This will be used to find the heat loss per unit length. We know delta T is equal to T1 minus T2, that is equal to 100 minus 30, which is 70 degrees. We can find R by the relation log of R1 by R2 by 2 pi L K. Let me put all the values here. This is equal to natural log of R1 is 0.075 meters, R2 is 0.05 meters by 2 pi, 2 into value of pi is 3.14 into length is taken as 1 meter square and value of K is 45 watts per meter Kelvin. This gives me the value of R as 0.00143. Now, putting this value of R here, I will get Q is equal to delta T by R. Therefore, Q is equal to delta T is 70, R is 0.00143. Therefore, Q turns out to be 48.95 kilowatt. So, this is heat loss per unit length. With this, conduction part is over. I will take the problem statements on convection and radiation in the next part of this tutorial. Thank you.